All right, today we've got a really cool puzzle for you. How do you find the area of a massive, super irregularly shaped lake using just one single measurement? It sounds totally impossible, right? But stick with me and you'll see how we can crack it together.
So here's how we're going to tackle this thing. First, we'll lay out the puzzle itself. Then we'll create a digital twin to find our clues. We'll find our very own Rosetta Stone to crack the code, uncover a really crucial twist when it comes to scaling, and then, finally, we'll get our answer.
Okay, so first things first. Every good mystery needs a challenge, and trust me, this one is a doozy.
Okay, so check this out. This is Campus Lake. And as you can see, it's not some nice, neat circle or a perfect square. I mean, look at all those weird edges and coves. How on earth would you even start to measure the area of a shape like this?
Now get this. This is the only piece of real-world information we have to work with. A single measurement taken in a straight line right across the lake. 1,182.39 feet. That's it. That is all we've got.
And that's the big question, isn't it? How can one single straight line possibly tell us the area of this entire complex shape? I mean, it seems like there's no way. But this is where things get really, really cool.
So, to crack this case, we obviously need more clues. And to get them, we're going to have to leave the physical world behind and jump into the digital realm.
So what we do is we create what's called a digital twin. We basically trace the lake's outline in a program called GeoGebra, and boom, we have a perfect digital model. Now we've got a shape we can actually mess with and measure. And once it's in the program, we can start pulling some data. See, in our digital world, that same line we measured earlier is now just 5.67 units long. And even better, the program can just spit out the area for us, 40.15 square units. Now, you're probably thinking, what the heck is a unit? And right now, it's nothing. It's totally arbitrary. But don't worry, these numbers are the secret key.
Okay, so now we have two different sets of numbers. We've got feet from the real world and these weird units from our digital model. They're basically speaking two different languages. We need something to translate between them, kind of like a Rosetta Stone for our puzzle.
And here it is. This is our big aha moment. The exact same line measured in two different systems. We know for a fact that 1,182.39 feet is 5.67 units. This one-to-one comparison, that's the link we've been searching for.
This link has a name. It's called a scaling factor. And honestly, the easiest way to think about it is like a currency exchange rate. If you know how many dollars are in 1 euro, you can convert any amount of money, right? Well, same idea here. We just need to figure out how many real-world feet are packed into one of our digital units.
And the math here is actually super simple. All you do is divide the real distance by the model distance. And what do we get? We find out that one single GeoGebra unit is equal to about 208.5 feet. This right here, this is our code breaker. This number connects our two worlds.
All right, we've got our conversion rate, so we're done, right? We just multiply the area and call it a day? Well, hold on. This is where the story takes a really important turn, and it's something a lot of people get wrong.
So the logical next step seems pretty obvious, right? We've got the area in square units, and we know how many feet are in a unit. Can't we just multiply 40.15 by our magic number, 208.5? The answer is a big not quite. And this is the absolute core of what we're talking about today. You can't just do that, and the reason is all about dimensions. See that number we found, 208.5? That's a scaling factor for length. And length is a one-dimensional measurement. It just goes in a line. But area is two-dimensional. It's got length and width. So to scale an area correctly, you can't use the 1D length factor. You have to use the 2D area factor, and that is always the length factor squared.
Let's make this really simple. Imagine you have a square, and let's say you double the length of its sides. Your one-dimensional scaling factor, k, is 2. But look what happens to the area. It doesn't just double. It gets 4 times bigger. It's scaled by k squared. 2 squared is 4. This simple little rule is everything.
Okay, now we get it. We understand the huge difference between scaling in 1D and 2D. With that piece of knowledge, we have everything we need to finally put this puzzle to bed.
So let's walk through the final steps. Step 1, we find our 1D factor, k, which we already know is 208.5. Step 2, and this is the crucial part, we find the 2D factor by squaring it.
So k squared is a whopping 43,472, roughly. And finally, step 3, we apply that number to our model's area. So 40.15 square units times 43,472, and that gives us our final answer.
And there it is. The total area of Campus Lake is approximately 1.75 million square feet. We actually did it. We started with just one single line, and using a little dimensional thinking, we found the area of the entire complex shape. Pretty incredible.
But come on, let's be real. 1.75 million square feet, that's a massive number. It's kind of hard to wrap your head around what that actually looks like. Is that big? Is it huge? To really get a feel for our answer, we need to put it into units we can actually picture.
And there you have it. It comes out to about 40 acres. Now that is something we can understand. Just for perspective, an American football field is a little over 1 acre. So we're talking about a lake that's the size of almost 40 football fields. Now we can really feel the scale of this place.
So think about what we just did. We went from a 1D line to a 2D area. This just leaves one final nagging question, doesn't it? We used k for length, and we used k squared for area. So what if you wanted to find the 3D volume of the lake? What do you think that scaling factor would be? Something to think about. Thanks for joining me on this one.